I'd like to talk to you today about the difference between linear and exponential functions. Specifically, I'm really going to deal with exponential functions, but in my first example, we'll do a standard linear function, and then we will compare the exponential functions and how they compare to the linear. What I really want you to understand here is the difference between growth and decay, how to find the growth factor or the decay factor, and how those relate to these functions in general. Let's go ahead and talk about the functions in general, and then I'll do a couple specific examples for you. One each, one growth function and one decay function. I'd like to start today's discussion with a comparison between linear functions and exponential functions. Now, linear functions, you'll remember, basically follow our usual form of y equals mx plus b, and we just need to find the slope and the y-intercept. Let's take a look at our first example here. On January 1st, 2000, a bank account has a balance of $1,000 and $100 is deposited every year. Let's give the equation of the function. Now, I'm going to assume that January 1st, 2000 is year 0. That is, the bank account has been open for 0 years. So literally, this would be 0. This would be after it's open for 1 year, 2 years, 3 years, and 4 years. Now, remember, the y-intercept is actually the initial amount that is in our bank account. So in this case, it's $1,000. And the slope is actually the change in y over the change in x. And frankly, if you look at this, that's going up by 100, the y column if you will. And the x column is going up by 1s. So our change in y over our change in x is 1,000 over 1, or 1,000. So basically, y equals mx plus b makes this equation y equals, and I'm sorry, I lied. It's going up by $100 every year, not 1,000. 100x plus the y-intercept, the initial amount was 1,000. Putting that into normal function notation, I am going to say that the balance after t years is equal to 100 times t plus 1,000. Let's talk about exponential functions now. Just like the last example, I have a bank account that I open on January 1st in the year 2000 with a balance of $1,000. But now I'm going to apply a 5% interest rate that I will deposit every year. So on January 1st, the year 2000, there's $1,000 in the bank account. That's essentially year 0. Now, after 1 year, on January 1st, I take 5% of my $1,000. That's $50. So now I have $1,050. Now you'll notice the next year when I take 5% of this amount, the interest that I earn actually increases. The next year the interest will actually be $52.50. And the next year the interest will actually be over $55, $55.13 if you wish to be specific. And notice it gets larger and larger and larger every year. That's because the balance is going up. This is the effect of compounding, which we'll talk about at a later date. But for right now, this is still basically 5% simple interest that is applied at the end of every year. But essentially that's yearly compounding that's going on then. So let's talk about this. If I started with $1,000, that would give me the balance that I have in the first year. If I want the balance that I have the next year, first of all, multiplying by 1, recall, does absolutely nothing. So if I want the balance in the second year, I multiply by 1, that just merely gives me my money back. I have to multiply by 1.05. Or if you think of this in percentage form, what I'm really saying is the second year, or in other words after the first year, there's 105% of the previous year's balance in there. If I merely got 100% of my money back, my balance would still be only $1,000. So I get 100% back, in other words every penny I deposited, plus an extra 5%. So I really have to multiply by 1.05 or 105% to find out what the balance will be the following year. If I want it after the 2 years, at the beginning of the second year, or the beginning of the third year, excuse me, I'd have to multiply by 1.05 again. And for the third year, 1.05. And every year I'd multiply by 1.05. So my basic equation would be my balance at any year in time would be my initial $1,000 plus, times 1.05 t times, where t would be the number of years that the interest was added to the account. So the standard form here would be this. If I want the balance in my account after t years, then I take the initial amount, I multiply by the factor that the account is growing at to the t power, where t again would be the number of years. Let's try a couple examples. Let's first try a growth example. Let's say that you have a bank account where you have $1,000 for an initial deposit, but after 5 years the balance in the account is $1,354.08. Find what rate of interest the account is paying. First of all, I'm going to start with my generic equation. The balance in the account after t years would be equal to the initial amount in the account times my growth factor to the t power. What I know in this case is after 5 years there is $1,354.08. That's equal to my initial deposit of $1,000 times my growth factor to the 5th power. Now let's go ahead and solve for f. First of all, I'll take both sides of my equation and divide by 1,000. For those of us who can really divide, the decimal point should be right there, not here. Now, to find the answer, I'll need to take the 5th root of both sides of the equation, and I now have f equals 1.62, etc. It goes on forever and ever and ever. And essentially, I think what I want to do this time is I want to go ahead and round it off right here. This will become 1.60625. Now remember that if the bank account merely had 100% the following year and each preceding year after that, there would be no growth whatsoever. If I multiplied by simply 1 every year, then no growth occurs. The amount that it is over 1 would represent any growth that occurred. So in this case, the amount that's over 1 was the 0.0624, etc., or approximately about 6.25% interest. So we'll say that this bank account is paying 6.25% as an interest rate. For my second example, we're going to look at a decay problem. In this case, let's assume that there is a patient that's receiving treatment for a tumor. The tumor is shrinking at a rate of 5% per week. Assume that the tumor was 50 cc's in size to begin with. I want you to give me a function that yields the size of the tumor after we'll call the tumor T, by the way, the size of the tumor, after W weeks. Let's find the size of the tumor after 10 weeks then. Let's take a look at our basic equation. Again, I'm going to say that the size of the tumor after W weeks would be equal to the initial size of the tumor times whatever my growth factor is to the W power. Let's apply this to this problem. My initial size of the tumor was 50 cc's. Now remember, the tumor is shrinking. If I multiplied by 1 every week, it would be 50 week after week after week. There'd be no growth, no decay, no shrinkage. In this case, the tumor is shrinking by 5%. So what we can say is, after each successive week, there's only 95% of the tumor left, if you will. So 5% shrinkage means 95% is left, so I will multiply by 0.95. So the size of the tumor after W weeks equals the initial size of 50 times my decay factor of 0.95 to the W power for however many weeks there have been. In this case, I wanted the value after 10 weeks, so I will substitute a 10 for the W. That means my initial size of 50 will be multiplied by 0.95 to the 10th power. Doing the arithmetic results in an answer of approximately 29.937 cc's. Now I've rounded to the nearest thousandth place. I want to caution you again that you should never ever round your answer until you're finally done and you have your complete answer, and at that point you may round.